Okay, so this is Chemistry 108, Chemical Principles 1 at York College. It's March 19th, 2015. We're redoing the lecture from February 24th. So now we're starting Chapter 3. Chapter 3 is calculations with chemical formulas and equations. So when we get started, the first thing we're going to learn about is atomic weights. Now we've learned about in an earlier chapter about mass numbers, right? And so mass numbers are the sum of the number of protons plus the number of neutrons in the nucleus of an atom. And the mass number gives you some indication of the weight or the mass of an atom. But it turns out that the mass number is just an approximation. So H1, as remember, is hydrogen 1, contains one proton because it's hydrogen, and no neutrons because the mass number is 1. It actually has a mass of 1.0078 AMU, atomic mass units. That is, it's not exactly 1. The mass number is 1, but the actual 1 AMU, but the actual mass is 1.0078. And if we look similarly at oxygen, in oxygen 16, this is the isotope of oxygen that has 8 protons and 8 neutrons. We would expect that based on the mass number to have an atomic mass of 16 AMU, has a mass number of 16, but the actual mass number, the actual atomic mass is 15.99559 AMU. So these numbers are very, very close, within a few thousandths of the mass number, which is a whole number. But they're not exactly the same. And it goes on. It's not just hydrogen and oxygen. It's every isotope of every element, pretty much, is like this. And the reasons why you don't get exact numbers, exact whole numbers, they're quite complex. It's not something that we'll talk about in this class. But we need to know this, right? This is a starting point. However, we need to go a little further. Because here we're just looking at individual isotopes, right? We're looking at hydrogen 1, or we're looking at oxygen 16. But as we know, nearly all the elements in nature are comprised of more than one isotope. And so when we think about how much an atom of whatever, hydrogen, oxygen, carbon, whatever element we like, and how much that weighs, we need to consider isotopes. And when we consider the different isotopes, now we're going to start looking at what we call average atomic masses. And this is what it means. So nearly all of the carbon found in nature is either carbon-12 or carbon-13. Right, way back when we were talking about isotopes, originally we also introduced carbon-14. Now carbon-14 is very, very rare. There's a very, very tiny amount of it. So much that for this example in this presentation, we're going to pretend that it doesn't exist. So nearly all of the carbon found in nature is carbon-12, carbon-13. Carbon has an atomic number of 6, so that means carbon-12 has 6 protons and therefore 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. So in a regular sample of carbon, such as you, right, you are, after the elements of water, primarily comprised of carbon. And so in a regular sample of carbon found on the Earth, most of it, almost all of it, is carbon-12. 98.93% is carbon-12. 1.07% is carbon-13. you add those two together, you'll get 100%. Right? And then a tiny, tiny fraction that's so small it doesn't even count in the significant figures is carbon-14. So almost all of it is carbon-12. Almost all of the rest is carbon-13. Carbon-12 happens to have, by definition, a precise atomic weight or atomic mass of 12 AMU. And it's precisely 12 because that's how the entire atomic mass or atomic weight scale is defined. It's defined as carbon-12 being exactly 12. So carbon-12 is the only one that's a whole number. Everything else is fractional, as in the previous slide. Carbon-13 has an atomic weight of 13.003355 AMU. So when you look on the periodic table, you'll notice that there's an atomic number next to carbon, which is 6, and there's an atomic mass or an atomic weight, which is not 12, not 13, not 13.003355, but is actually 12.011, right, for the atomic mass of carbon. So typically this is what it's going to look like, right? Carbon and 6. So you're going to have the atomic number, the element symbol, the element name, and the average atomic mass. Where does this number come from? Because it's not this, right, and it's not this. I'm going to show you where it comes from. It comes from a weighted average of the carbon-12 and the carbon-13. The weighted average is different from a regular mathematical or arithmetic average, where you would take this number and this number, add them, and divide them by 2. That's not the kind of average we're looking at. Why don't we use that? Because these two are not equal in abundance. There's a lot more of the carbon-12, so we're going to take into account a lot more of the carbon-12, and there's a lot less of the carbon-13, so we're going to take into account a lot less of the carbon-13. Why do we need an average? Why can't we just say, okay, the carbon-12 is 12 and the carbon-13 is 13.003355? That's because in most situations, such as you, or in most cases such as you, it's very, very difficult or almost impossible to separate the carbon-12 and the carbon-13. They're mixed up. They're mixed up entirely randomly, and we can't pick out, you can't go into your cells and your proteins and pick out the carbon-13 and leave behind the carbon-12. Most of the time, the best we can do is, take a whole bunch, a few grams, a few milligrams of tissue or something, and in that, there's going to be this distribution of these atomic weights. So, in order to find the average atomic weight, this is what we're going to do. We're going to take the 12 AMU, that corresponds to the carbon-12, and multiply it by the percentage of carbon that is constituted of carbon-12. So 12 AMU times the 98.93. And to that, we're going to add the 13.00, et cetera, AMU times the percentage that is constituted of carbon-13, the percentage of carbon that is carbon-13. And when we do that addition, what we're going to get is the average atomic weight, or the average atomic mass. One thing to note that is, what does the percent mean? The percent means cent, like 100 cents in a dollar, means 100, right? So per 100. And so what we're going to do to convert these into numbers that we will actually use in our calculation is we're going to divide those numbers by 100 to get rid of the percent sign. And so we go after dividing by 100, we get 12 times 0.9893 plus 13.00335 times 0.0107. And that's a mistake that students often make, because they say, oh, okay, I look over here at the 9893 to get to here, I basically just get rid of the decimal place, or put the whole number behind the decimal place. Here, if you put the whole number behind the decimal place, you're only dividing by 10. You need a leading 0 here. Right, so it's 0.0107. When we do the math, we get 11.8716 plus 0.13914. And you add that together, and you do indeed get 12.011 AMU, which is, according to the periodic table, the average atomic mass of carbon. So what you would do is basically take a weighted average here. So reminder what we did. We set up the problem. We divided by 100. That converts to decimal, from percent to decimal. And then we did the addition, and we got a number and a unit. Right? For an atomic mass, or molecular mass, which we'll learn about later, some people call them atomic weights and molecular weights, we have, like basically all of our measured values, a number and a unit. And the unit for the time being is called AMU. Right? We've talked about that atomic mass unit. We'll do a calculation. We might do calculations like this down the road where we have a different unit, but keep that in mind when we get to that. Remember this. Here's another example. Right? Nearly all of the hydrogen found in nature is either H1 or H2. Right? H1 is regular hydrogen. H2 has the common name deuterium, you may remember. And so in a regular sample of hydrogen, 99.985% is hydrogen. And hydrogen 1 has an exact atomic mass of 1.007825. The rest of it, which is quite small, is deuterium. And that's the atomic mass of deuterium. So what are we going to do? We're going to set it up the same way. We're going to do 1.007825 times that percent plus this 2.01, etc., times that to get our initial setup. Then we're going to divide by 100 to convert from percent to decimal. Then we're just going to do the math. And when we do the math, we get 1.0079 AMU. And so just a quick review of the significant figures, right? So how many significant figures are in this green calculation here? Well, it's multiplication, so we're going to count significant figures and take the and round our answer to the fewest out of these. So this is 1, 2, 3, 4, 5, 6, 7. Those are all significant. 7 in the atomic mass, and 1, 2, 3, 4, 5 in the percentage. And so 7, 5, 5 is smaller. We're going to round this to 5 significant figures, 1, 2, 3, 4, 5. Similarly, with the pink calculation here, we have 1, 2, 3, 4, 5, 6, 7, and 2. So we're going to round it to 2 significant figures, which is the point where we get the point 0.00030. So 5 and 2, that comes from above. Then at the addition step, recall addition and subtraction, we're not counting total significant figures, we're counting decimal places, right? Columns after the decimal point. So here we have 1, 2, 3, 4. Here we have 1, 2, 3, 4, 5. So we're going to round off to 4 decimal places, which is going to give us the 1, 2, 3, 4, 1.0079. So that's the average atomic mass of hydrogen. Right, not too bad. It gets a little, just a little more difficult. And I'll show you an example of how. In this case, we're given the 2 percentages, and we're given the 2 atomic weights. What if instead of that, we solve for the average? What if instead of that we were given the average, and we had to find out something about this, or something about this. We can do that. And once you understand the concept, once you understand why we have to, or why it's important to think about average atomic masses, then it's just a matter of doing algebra. The algebra does get more complicated, or the math gets more complicated. So naturally occurring chlorine has two isotopes. This is true, right? So 75.77% of the chlorine found in nature is chlorine-35. What is the atomic weight of the other isotope? Well, if we were to set this up just with this information, like we did in the previous two slides, we would say something like this. Okay, so the first isotope has an atomic weight of, or atomic mass of 34.968853 AMU, and the percentage is 75.77. And then we're going to plus, and we're going to say it's plus the second isotope's exact atomic weight or atomic mass. But wait, we don't know that. That's what we're trying to find out, right? What is the atomic weight of the other isotope? We don't know what it is. If we don't know what it is, well, we'll put it in X. X times what? Well, if 75.77% of the chlorine found in nature is chlorine-35, and there's two isotopes, the other isotope must be everything that's not chlorine-35. So it's going to be 100, exact number, right, minus 75.77. Because this is an exact number, we can just, keep adding zeros, 0, 0, 0. And when we do the subtraction, we're going to get 24.23%. So this is total. Total, of course, is 100%. That's what you want to get on your exam. 75.77, that's chlorine-35. And this is chlorine X. And that's what we're going to put in here, 24.23%. Now we're going to do the math, right? We're going to divide each of these by 100. We're going to get 34.968853. And once you get the hang of this, you won't have to necessarily rewrite everything every time. You might go straight to this step. Plus X times 0.2423. Oh, and I have it on the slides. So when we do the math, we get to here. Right, we get to 26.496 plus 0.2423x. Oh, we forgot something. It equals something, right? We can't find our x unless it's an equation. Otherwise, we can't solve for x in an equation. If we have an equation, we know how to solve for x. What does it equal? It equals the average. How do we find out what the average is? Well, we look at the periodic table. And the periodic table tells us that chlorine has an average atomic weight of 35.45 AMU. So we're going to say equals 35.45. And how are we going to solve this? Well, we're going to try to isolate our x. We're going to do minus 26.496 minus 26.496. And we'll do the rest on the slide. So we did the subtraction. We got 8.954 equals 0.2423. X, we're keeping an extra significant figure temporarily until we get to our final answer. And then to solve for x, what we're going to do is divide by 0.2423. And we're going to get 36.95. So the second isotope, the atomic weight of the second isotope of chlorine is 36.95 AMU. And because the whole number that it's very close to is 37, we're going to say that the other isotope is 37 chlorine with this exact atomic mass. Okay, so there's lots of different ways that we can do that. We can think about doing calculations. We'll do some more of these to practice down the road. We'll hope that you also do about 10,000 by yourself as part of your homework. And we're done here.